Fritz Röpke, whose name I can't pronounce, in simulations of supernova type 1a simulations. He then moved to Heidelberg 2010 to do his postdoc with Volker Springel, with whom he then formed a dream team, kind of, and continued to develop a repo. He's like one of the core developers of the repo. And together they also like performed several flagship simulations, such as, or they helped performing them, Illustrious TNG, Millennium TNG, the Auriga simulations, and now he's going to talk about Auriga Superstars. Thank you very much.
Thank you, Rebecca, and thanks for coming, and thanks for having me here, and thanks for trying to stay awake for an hour or so while I try to tell you about these simulations. And so this, as Rebecca said already, this Auriga Superstars, I will kind of like start from the very end first. What you see here are kind of the movies of the first round of kind of final production runs. And so these are Milky Way mass cosmological zoom simulations. And what you see like very nicely in these movies already, and we will look into much more detail later, how this works and what this exactly is that they have like very high mass, in particular, high mass resolution, in particular in the stellar component. So you really see like all kinds of like fine structures in the stellar light and can like analyze them hopefully in like quite a lot of detail. And I will show you a few more quantitative and specific plots of the very first things we have started to do there as well. Importantly, this is only one of the people involved in this project. The list of the main people involved this year is Francesca Fragudi, Robert Grant, Rebecca here, Facundo Gomez, Christine Simpson, Wilma Trick, and Freke van der Voort. And so this is we've been working on those on and off for like several years now, usually because while everyone is really interested in those, it wasn't necessarily highest priority for everyone. And so like it always like kind of like makes things in like leaps and steps, makes progress. Okay, so the idea is really to improve the modeling of the stellar component in cosmologic simulations. And so this is not okay. Yeah, so just as the overview for this talk, I will try to give you a very brief motivation what we do there, the zeroth order, why we want to do this and what we aim for, like kind of in terms of science that should come out of this eventually, that is not just really nice movies. I will then give you a very brief introduction into the base, like kind of the base model, just that we are all on the same page. That's the outcome, that's still from the Auriga cosmological zoom simulations that have been around for a few years now. Then I will discuss kind of as a prelude to what the new thing we do here, some kind of systematic analysis of both convergence of the Auriga model and robustness of the Auriga model. And I will go into more detail of what I mean with this. Then I will show you what the new thing we do here. And then I will give you a first glimpse into like some kind of results of these new production runs to see what we can actually do with this and what's the starting point for this. So the main motivation is really stellar structures in Milky Way-like galaxies. And so the kind of like in the last like several years or so, a lot of this has been completely revolutionized by Gaia. Gaia now giving us like proper motion and 3D coordinates of a lot of stars. And so, but this in particular means you can like not much more cleanly like figure out structures, stellar structures in the Milky Way. And so here's like two nice examples that I will go back to at the very end. First, what you see here is a plot of like stars in tangential versus radial velocity in the solar neighborhood. And you see these kind of like, essentially these are called moving groups because it's like a velocity plot. And so these like kind of think like groups of stars that move in a correlated way. And so essentially the question is like, what are these exactly? What's the physics that like creates them? What do these mean and so on? And so we would like to like model, to have something like this in a cosmological simulation to understand how these could potentially be explained. So this is like, these are like features in the stellar disk. And then like the other kind of relatively, or the other kind of really important plot is not only looking at structures in the disk, but structures in the halo. And so this is just like stars in like here now in like energy versus angular momentum space, also in the solar neighborhood, but with some velocity cut, so it cuts out the disk. So these are really like substructures in the halo, and you can like see the names of all kinds of things, and essentially there have been papers written on every individual of the ones of these like of these structures in there. And also there we would really like to understand in kind of in a cosmological context what these like how these are potentially explained, what the properties of these things are, whether what we see here is actually consistent with predictions of cosmological simulations. And one of the things that's kind of important for both of these say is that these are not super massive structures, right? So this thing here has like this whole plot has a few 10,000 stars in there. So the whole stellar mass you see in there, like a few 10 to the 4 solar masses, maybe 10 to the 5 solar masses. So if you want to look at anything like this in a cosmological simulation, you really need like a stellar mass resolution that's enough that you have information in those scales, right? So that you need like high mass, like if you ever go to this with a mass resolution of TNG 100, like 10 to the 6, or even TNG 50 of like few times 10 to the 4, like 8 times 10 to the 4 or so, like there's like just a handful of points in this plot, right? So like this type of analysis you can just forget about in the cosmological box simulations. And then last but not least, we're also really interested in like the large dynamical structures in Milky Way-like galaxies, in particular in the bar, and how bars form, how bars evolve, what's the physics that drives bar formation, and like the changes to bars, and like more like the kind of more complicated version, what forms spiral arms, what are spiral arms even, is like, are all spiral arms the same thing, or the different types of spiral arms, and so. And so also for this, the one of the critical ingredient is just like brute force mass resolution. And so for both, because like there are kind of two main reasons where mass resolution helps with this in the stellar component. First, you just have more traces for things. So you see things in more detail if you have higher mass resolution. And the second one is kind of a more subtle point, is that if you have better mass resolution in the stellar component, you also have a smoother potential. So you beat down the Poisson noise that you get from the particle distribution. And so in the end, there's some hope that with higher mass resolution, also the finer structures are resolved better, and the physical perturbations at some point dominate over the purely numerical perturbations. Although that's in practice, we will see like a hard point to show explicitly. Just as a rule of thumb, for example, like Elena Dongia has shown like 10-ish years ago or so, that if you set up like an isolated Milky Way-like disk with like less than about 100 million star particles, then even if you start with 0 perturbations, you just form from random noise spiral arms, right? So you need about 10 to the 8 particles in the disk for numerical noise not dominating the effects. Okay. So really want higher stellar mass resolution for the things you want to do. Now, these things are based on? So these are based on the Auriga cosmological zoom simulations. So this is a cosmological zoom simulations means that we really start from cosmological initial conditions at high redshift. So we have a 100 megaparsec box, 100 megaparsec cube box. We start at redshift 128. The initial conditions are like very well defined. We have periodic boundary conditions, and then we evolve the thing all the way to redshift 0. Now, the trick with the zoom simulations is rather than having kind of like homogeneous resolution in the box, we throw all our resolution elements in like a small sphere with the radius of just a megaparsec around one halo of interest, right? So like we pick like the region where like a Milky Way will form eventually, and just throw all the resolution elements there, and just model the background arbitrarily poor resolution, like it's still there, but it's really poor resolution, just enough to get like the large scale tidal gravitational field correct. And so with this, we can reach like way higher resolution than if we would do like a cosmological box like Elastis TNG or so, where we essentially have homogeneous resolution all over the box. The downside is, of course, that we then per simulation only model one halo really, one main halo really. And so we have to then do several of those to get a little bit of statistics and understand like whether a feature we see there is essentially a chance thing or whether this is a systematic difference itself. Okay, the galaxy, so these are simulated in the moving mesh called the REPO. So it's ideal magnetohydrodynamics plus gravity plus what I would call a galaxy formation model, which essentially tries to, in an effective way, include all the physical processes that you need in baryons to form a galaxy. And kind of like the brief summary is that you need some kind of radiative cooling, and so there's primordial metalline cooling included. We have like an effective model for star formation and ISM. So once the gas reaches a certain density, the kind of ISM becomes pressurized in our simulations, and we allow stars to form. And these are the these form star particles, and the star particles also kind of from tables that models like what we think of how stellar evolution works. We include like mass return and metal return back from the star particles to the gas. We also, and so this is will be a crucial thing that's slightly different than than a number of other cosmological simulations. We have an effective model for galactic winds. So what this means is, so like everyone who has tried to simulate a galaxy already knows that if you don't blow out it's like gas effectively over cosmic history from the galaxy, then we will just overproduce stars. So this to how this physically exactly works is still relatively unclear in detail, right? So there's like lots of discussions, a full topic of active research. But if you want to do this really well, the mass resolution, even in those simulations that we have, is insufficient to do this really. So rather than trying to do this directly, what we like trying to model how the wind forms, we just assume there is a galactic wind, parameterize it with like a handful of parameters. Typically, what we set is the velocity of the wind and the mass loading factor. So like how much mass goes into the wind relative to into stars. So it's relative to the star formation rate. And then just like have a model that just makes this wind happen with these properties. Then we also have like a model for black holes, for the seeding, for the growth and their feedback, which is like for these types of galaxies. In this model, it has an effect, but it's not a dominant effect, right? So you have to go to slightly more massive halos for this to really be a large effect. We also have magnetic fields in there, but they are like not super relevant for what I showed today. And then just to put this into context, so these simulations originally we published those in 2016. We had like a set of 30 halos in what we call level 4. So this is a baryonic resolution in gas and stars of 5 times 10⁴ solar masses. And so if you do this, you have 2 million star particles in the disk energy. So we had a set of higher resolution simulations, only 6 galaxies because they were quite more expensive already, at a mass resolution of 6,000 solar masses, a factor of 8 better, and then you have 15 million star particles. But what you really want, like just going back to the numbers, is to go to even higher resolutions. And so to reach like the 100 million particle level, we need like at least one level effect of 8 higher resolution, so going to like 800 solar masses. And then, of course, if we would like to go even higher, but like you do what you can. Okay, so we have tried this, and this kind of works well, and so we want to go to higher resolution. So the first thing we can try to do, just do it brute force, right? Go to higher resolution in all components, gas, stars, dark matter. And then what you see there is that we run into not drastic, but like relevant enough convergence issues. And so what you see here is stellar light projections of the same halo at redshift 0 at 3 different resolution levels. So this is the standard resolution, 5 times 10 to the 4 solar masses. This is one level worse, 8 times vector worse resolution, and this is 8 times vector resolution. And what you see here already by eye, and I will quantify this in a second, is that the total light you get just becomes more at higher resolution, right? So, which essentially means you form more stars. And so now, if you see this by eye already, like for the things that we want to do for the detailed stellar analysis is obviously an issue. And now you can go quantify. And so first you can ask, is this something that happens just at high redshift or just at low redshift? Like, is this like a specific problem I can somehow easily fix? And the answer is unfortunately no. So what this shows is the star formation history for the same halo now at like actually 5 different resolution levels. So we have a factor of even worse. And we actually ran this one halo with a full mass resolution of 800 solar masses to redshift 0. It was quite expensive. Also, it was like not great because this, as you see, the star formation, like the star formation rate just goes up kind of at all times with higher resolution. And you can then quantify by how much this is. And so what this is just a plot of the stellar mass at redshift 0 versus the mass resolution and like the mass of the baryonic mass resolution baryonic component. And what you actually see is that very consistently the stellar mass goes up by like 30% for a factor of 8 in mass resolution until at the very end it's like slightly less. But at this point, you're also so high in stellar mass already that you're like changing the gas reservoir of the disk is substantial. Yes.
So what are you doing to the, it's the same star formation recipe?
Yes, the model is completely the same. Yes. So it's really it's as good as an attempt for convergence you can do. We do not try to add any additional physics on smaller scales that we might resolve. Right? We just take the model flat value.
So even the star formation recipe.
It's the same.
So what about the galactic rates? So they depend on star formation rate. So then
yes.
you have a self-regulation.
Yes, exactly. So you would hope that it compensates for some, and it does, but it doesn't do it. You still get systematic trends. And I'm not going to go in detail where there's I think we have a reasonable understanding of where this comes from. It's not easily fixable, and we can discuss this later if you want. But for now, let's just accept that this approach doesn't work for what we want to do. Because in the end, if you go back to things like we want to look at like a bar formation, for example, or so, that really very sensitively depends on the stellar mass in the center of the galaxy. And if you rerun a galaxy that has reasonable properties at much higher resolution, and we just get like 30% or like twice 30% more stars, then this is just a very different galaxy, right? So we can't do really any resolution study or even any extrapolation of what we would get there. And then this is also not super surprising because we have exactly the same issue in TNG if you look close, right? So from TNG 300 to TNG 100 to TNG 50, the stellar mass at fixed mass goes up by exactly the same factor. So this is a relatively general problem. Okay, now having accepted this, one question you might ask is, so this is about the convergence, right? One question is about the robustness of the model. It's a very different question, and it's essentially asking, how good can I possibly expect this to ever get? Right? And so in other words, you run the simulation, and how chaotic is the result? So if you run this marginally differently, how similar will the results still be? Or do you just go do branching path and end up something very different? And so there's different ways of doing this. The way we approach this, just to get an understanding of how robust the model is by just simulating the same halo at the same resolution with the same initial conditions with different random number seeds. And so the random number seeds really go to, for example, in the star formation, when you decide whether you make a star particle or not. But there's also a few numerical if the mesh construction has to at some point decide, because it's there's a degenerate case of the Voronoi mesh, how it exactly defines the mesh, then there's also some randomness in there. And this is of course, any of these things are equally good results. It's in a way, but the round-off error might be different, right? Because the ordering in which you add numbers are different, and so you get like slight noise in your system. The same happens, for example, if you run the simulation on a different number of courses. If you run it on the same number of courses with the same random number seed in a repo, you always get exactly the same result. So that doesn't, right? So the result on the same machine with the same number of courses is fully deterministic. Okay, so we did this, and so this is now at the standard resolution. This Halo 6, our standard test Halo, for 7 different random number seeds. So it's the same Halo, same galaxy. And so it should really be the same galaxy, right? And so already, there's like 2 main takeaways from it. So first, the brightness of those is actually very similar. And the radius of those is actually very similar. So you actually, and we can quantify this in a second, but so overall, these things are actually very similar. However, what you also see immediately, that like the detailed structure of the stellar component is very different, or they can vary a lot, right? So some of them have like a bar-like component, others have like just don't at all, and the spiral arms are generally all over the place. And so what this tells you is that at least at this mass resolution, both of these things are relatively, like at least for this galaxy, relatively noise dominant. Just to mention, so this bar-like thing is really only bar-like, so it would not, like a weak enough bar that it would not cross any, this is an actual bar criteria that we would typically use, right? So that's also why it's like so noisy, essentially, like sometimes there, sometimes. If you do a similar exercise for galaxies with an actual strong bar, then the things are actually much more well-defined in the image, but this is a difference. But yeah, so essentially the global properties look good, but the structure of the stellar components is seems to be not super. Yes.
This based on the so you change random seed.
Yes.
So typically what that means.
So
it's changing cosmology.
No. I start with the same initial conditions, with the same phases and everything, right? And then and I just like generate them before with my initial condition with engine IC or something. And then I start the repo simulation, and the random number generator that I use in a repo has a different seed. And where this is used, it's actually mainly for the stochasticity, for the stochastic star formation, right? So the first time I form a star particle, it will then form a different cell than in the other, right? And then the metals will be dumped somewhere slightly differently, and so right. And so then it's still like from the physical equations a completely equal representation. It's just the realization of it is different. Okay, then we can look at the same plots as before. So this is the star formation histories. And also that there you already this looks much better than what we saw before, right? So I've not color coded them here because these lines are all like equally relevant, or like there's no preference to any of those. But you see that essentially the whole at very early times the resolution is actually very, very similar. And then you get a little bit of noise, but the noise actually there's never any substantial systematic difference here, right? And the star formation rate at redshift 0 is relatively uncertain by at least a factor of 2, which is mostly because it decreases towards redshift 0 so much compared to what it was, right? So if you take this the current star formation rate at the last 100 mega years or so, that is not a very safely predicted value either of the simulations. Now we can also look at just the total stellar masses at redshift 0 of the galaxies. And so again, this is the same x-axis that we saw before, where this thing was all over the place. Here now we see that we get really nice, very consistent stellar masses. And so the kind of the deviations here are actually on a few percent level. So the total stellar masses are always the biggest difference is still better than 10%. So what this essentially means that there's at least a chance to do what we want to do, right? So because if the stellar masses here would also be off by 30% or so, then the whole thing would be obviously so random that it would be very hard to go to higher resolution and even compare different resolutions. But this is not a principal problem. Okay, so what we do in Auriga Superstars. Again, we want to mainly focus on the stellar component and increase the mass resolution in the stars, just to have more star particles, more tracers, smoother potential from the stars. And so if we change the gas resolution, we get a different galaxy. So we don't. So we keep the gas resolution the same. We stay at the resolution of the standard Auriga model, which is 5 times 10 to the 4 centimeters. What we do, however, is we increase the mass resolution in the stellar component. And for the production runs I showed the movie of in the very beginning, or like also for this example, we change this by 2 levels, so it's a factor of 64. And the way we do this is by every time when a cell forms a star particle in a normal simulation, rather than just forming 1 star particle, we just put 64 star particles at the identical position and give them a tiny velocity dispersion that we essentially sample from a Gaussian with a width of the sound speed of the cell. It's typically a few kilometers per second, so that they are not bound to each other. And so then they essentially generate 64 independent tracers that give us like also a significantly smoother potential. The other advantage, and so there we come back to the way how we do the galactic winds, is that because our galactic winds are really like an effective model that's completely decoupled from the actual star particles and any actual stellar feedback, we can still do the galactic winds in exactly the same way as we did before, right? So because we do them by rather than making cells into stars, there's some cells that are transformed into wind particles instead. And this, we just do it exactly the same resolution in the exactly the same way as in standard Auriga. So the feedback doesn't change. The ISM model doesn't change. It's really just we get more star particles. One interesting side effect is that because if we go to 64 times higher stellar mass resolution, we have 60 times more star particles. These are so many particles that we suddenly have more star particles than dark matter particles. So we can increase the dark matter, we can improve the dark matter resolution also by a factor of 8 without actually having to pay any significant additional price for this. Because the star particles usually are smaller time steps than the dark. I need to check. I think we go to slightly smaller softening with the star particles as well. But like, yeah, I think at most a factor of 4 for the 64 resolution. We tried in the past. It seems to be at the softening that we use. There's a bit like it has very little effect if we fiddle this a little bit. But we are typically at a relatively conservative softening. So the default softening for level 4 Auriga is actually for stars is 300%. Okay, so how does this work? So again, as a reference, this is how the galaxy changes when we change the resolution of the gas as well. Now we can now do so in this thing. We only change the resolution of the stellar component. So mass and dark matter are the normal resolutions, and we increase the mass resolution in the stars by a factor of 8. You see that the 3 galaxies all look very similar, which is good, and we can then quantify this in detail. But also the cost only goes up by about 50%. Yes.
Sorry,
So these are 3 different realizations again. So I can say. So for all the additional ones, then we ran 3 different realizations as well with 3 different random number seeds, because otherwise it's like too easy to like talk yourself into like this difference is marginal or not, right? So we really have like statistics for all of the additional tests we did. Because yeah, like it's single object is very hard to interpret. And then as another example, we have here the one where we, rather than going up with the stellar mass resolution, we go up with the dark matter resolution. And also this kind of like, this is kind of a probably even more obvious point, doesn't change the galaxy at all. So like also there, if you, so this would be the reference for those, right? So this also is very similar. Yeah, so this is a good question. And it's in the end, in a repo, it's really simple. What we do is we start with the better initial conditions for the dark matter particles. split this and split the dark matter. So we always have dark matter only ICs, and then at the very beginning, we split the dark matter particles into a dark matter particle and a cell. And then if we want to like run, essentially what we do here is like, so this is the starting point, and then we want to do the gas at lower resolution than what the split gives you. And so we just de-refine the gas. And so because a repo can like very quickly, very efficiently, and actually very accurately do the de-refinement, so we just tell a repo that the target gas mass is a factor of 8 larger than this, than what it starts with, and it just does this within a few time steps. Yes, and a particle code is way harder, because then like the de-refinement you need to think much harder about, right? But in a repo, that's actually like both refinement and de-refinement is like a well-defined operation. Okay, and so then we can just look a little bit quantitatively. Again, this is just for the stellar mass here to give you an impression. And so essentially what you see here, so these light points are all the different variations, and then these points are like kind of the median and the percent, I think this goes 20%, 80% percentiles. And so for essentially as long as we don't touch the gas resolution, we just keep a very consistent galaxy. And only if we go to lower order or higher gas resolution, then the stellar mass actually changes substantially. If you don't do this, then the stellar mass really stays consistent with the value that we had initially. Okay, so having convinced us that this kind of works, we have like more of those plots, but I'm not going into detail here. The method paper about this will hopefully be out, let's say in fall. Like, but so we're working on this, but it's not there. Okay, so we've convinced ourselves that this seems to be a reasonable idea to do, and so we actually ran a set of production runs. 8 Milky Way-like halos. We took them all from the original Auriga sample, so we also have the original simulations to compare to, or the original results to compare to. And essentially what we do for the setup is we stay at the default Auriga gas resolution. We go to like 64 times better stellar mass resolution and 8 times better dark matter mass resolution. We also have an additional thing that's called dwarf refinement that I will not go into detail here, where if the halo is below a certain halo mass, we actually also go to 8 times better gas resolution. Because in particular for the low mass halos, you actually only like there's a limit where you don't form stars at all in them if you don't resolve the gas at all, right? Because you don't have enough cells and then you don't sample the potential well enough. Yes.
So another question to understand.
Yeah.
So if you say you only increase stellar resolution, what do you do when you create a star particle?
Yes. So what we do is essentially we do like at the point where the code says I'm creating 1 star particle, rather than creating 1, we create 64. Put them at the exact same position and give them a tiny velocity dispersion. So they start from the identical position, but with with the same bulk velocity, but a tiny offset on the velocity, so that the total velocity we add is 0. And so this is like of order kilometers per second. Okay. So we can first so as a first look again, so like this is for 6 of those, you saw the movie before. The movie doesn't have the 2 new ones yet because rendering one of those frames is like 2 hours or so. Because there's so many star particles that doing this is like super long. Like, we will have a movie with like all the halos eventually. But what you can see, so again, what you can see here, this is like a spectrum of like where they're all Milky Way mass halos, and they're all disk galaxies, but they kind of are in their properties quite substantially different. We have some barred and some non-barred galaxies, right? So like there's one with a strong bar here. This one has a strong bar. Some have like a little bit of a symmetry, and some of them have like no meaningful bar at all. What's also interesting to see, and we haven't looked into this in very much detail yet, is that they actually have seemingly different types of spiral arms. So this one here is like a classic like 2-armed thing. And so there it's actually, if you look at the movie and if you look into detail, you actually see it very nicely. This comes from a recent interaction with a very massive neighbor. So it's really the classic, like it's like a flyby of a massive thing that will probably emerge in a few giga years or so. And so this gives you these 2 arms. But then you see that like, so there are things that are like this one here that's more like flocculent or so. And then there are other things like this one here that really has like very tightly wound, whatever things there. And the cool thing is really that we now have the mass resolution and the statistics there to try to really understand this in detail of at least what happens in the simulation. God knows whether that's the same thing that happens in the real universe, but the way we can like, understand how these features are created and what's the physics that makes those features in the simulation. What we also did to like make this somewhat easier, so these galaxies all have like more than 100 million star particles then in the disk at redshift 0. We also wrote out the stellar properties with really high temporal cadence. So we have like essentially 5 megayear cadence snapshots of only the properties of the star particles. So we can really look at every stellar trajectory individually. It's a huge mess to deal with from the amount of data, but it's really like we can really go and look at like bar orbits and non-bar orbits and try to understand whether the spiral arms are an orbit thing or not, and so. You can also like, it's interesting to compare this to the original ones. So this is the original Auriga simulations of the same halos. And so you see that if you flip forth and back, some of them actually very similar. The one on the bottom right does whatever. We still have to understand why it just looks completely different. But the other ones are actually very, very similar. Or like some of them similar. This bar is also interesting because this, like in the top right, that has, like in the original ones, it had this relatively strong bar, and here it completely goes away. But then the two, on the top, the two middle ones, essentially they are very similar, and also the bar looks very similar, right? So the result seems to be very strong. Okay, we can look at like a little bit more quantitatively into the star formation histories. And so the black line is now the new simulations, the gray line, slightly lighter, is the original star formation history. And also there you see that these are like very, very consistent with each other. So it's really a galaxy, the galaxies form, and as we intended, form their stars in a very similar, at least temporal way, and with the same, very similar stellar mass. So the numbers here give you the stellar masses. And so typically they are also within a few percent of each other, even though we go to this much higher stellar resolution. Also, the dark matter resolution doesn't seem to change this at all, really, which is a more subtle point, but it's also interesting. Okay, so what can we do with this now? And I'm just going to flash like a few things. So one of the things, if you want to, like I've showed you this moving group plot before. And so what we can do now, we can take one of these galaxies. We just do pick a reasonable solar position, take the stars within a certain radius, and do the same by, in this case, versus radius. And so what you see now is if you look at the superstars, and yeah, so I think this is slightly better. We see all these like kind of stripy structures in the order. It's really good. We have the statistics now to really go and analyze them and categorize them. But in the original simulations, like if you really squint your eyes, maybe you can dream of having something like this as well. But there's like no way that you go and interpret this really as like as a structure. So this is really nice, and so it's at the minimum, it's the significantly better statistics already allowing us to do things. Now, we can also look at this like substructure plot, and so this is like a slightly simpler version than the one from the observation. So I just took all the stars within a certain like radial annulus, so like between, I think it was like between 7 and 9 kpc from the center of the disk, and within like 10 kpc height or so. So this is what you see, this black thing here is usually just a disk. And now you can, so this is for the original Aurigas. And so yeah, you see like there's some where you see a little bit, here's a feature and there's maybe something there, but it's really like tiny smudges and it's like very hard to see any detailed substructure. Then you do the same thing for superstars. And you really see like very nicely all kinds of like well-defined features that are really like will have some properties, and then you can now go and like really identify them there, trace them back, figure out, did this come from a satellite or did this come from something else, or really what made this, right? And so also there are probably two effects that are critical. The first is the better mass resolution just gives us more traces, right? So like, it's just like the other thing is like very noisy compared to this, right? So like just it's almost effect of 100 better mass resolution. So 64 times more star particles. But also because of the smoother potential, we probably have an effect. And it's hard to quantify this in detail, but we probably also have an effect that because of less noise, we just have less phase mixing and we lose these structures more slowly, right? So they will probably remain long. Now, this is for like structures kind of in the solar neighborhood, and the way you usually then want to look for like halo structures locally or so. You can also try to do this for like external galaxies. And so this is a plot of showing, so this is now much larger scales, like slightly zoomed out. So this is 50 kpc. So the whole thing is, I think this goes out to like 100 kpc on both sides or so. And what you see here is, yeah, so the background color coding is the stellar mass surface density. And where the stellar mass surface density goes above 10 to the 7 solar masses per kpc squared, I just overplotted the stellar light so that you see the galaxy and it looks nice. And that's actually like, there's a super nice platform of service that did exactly this, I think. So the idea is completely stolen. And also here you see like a little bit of structural features, like in the halos here, there might be something here. Yeah, you see like some kind of shapy arms, but they are very blurry because in the end you don't have the resolution statistics to do this too well. Now you do this with superstars, and you really see like very like, let's go to the better view. And you really see like very nicely kind of sharp structures there, like sharp shells. You also see like here, this feature now is really like a nice kind of like bony sharp thing. You also see here, like where the satellite seems to be stripped, like it has like an arm here and an arm here, and you really can go now in detail and look in like how this, not only how this like analyze it, how you see it redshift 0, but also in detail how this evolves over time. Yes.
So it's very surprising these underlying rings of these cosmets.
I think this, so they have been seen in observations for much more massive galaxies, right? So like in clusters, they're like a relatively clear thing from like in the ICM, in the interstellar light. And I think the most they come from destroyed satellites that are then phase mixed, but like keep their conserved quantities, right? So they keep like they come in with a certain angular momentum and energy, and then they're just like smeared out essentially at a certain radius.
Also happens from the radio physics.
Yeah.
Most of the orbits produce fast fidelity characteristics, near the radio orbits produce flat. Yeah. Yeah, of course. But the turnaround radius for the subsequent case.
Yes, it's also, yeah, most of them only have like 1 or 2 or 3, right? Like so, but we can, but in like not only, yeah, so not only can we look at them in detail here, but we can then also go, we can actually ask for all the star particles that makes this, right? Like from which satellite did it actually come, right? So they can in principle even split this into progenitor satellites in relatively straightforward ways. I haven't looked. Might be. Because it's like impossible to observe in dark matter.
Yeah.
Well, if the caustics may be right, but yeah. Okay. I'm already relatively far advanced in time. So like one of the things I will just flash very briefly, one of the things we can also use this for kind of as a side effect. So like because we have lots of information about the star particles, we can first like look at, of course, not only when were stars formed, but at which radius in the disk. We can look at like how much they moved in radius. But now what we can do in addition, that's otherwise not possible, we can look for the stars that were born together. Like how chaotic, like how much do they actually spread, right? Like so essentially how or like how chaotic is the spread of the stars that were born together at the same place, and like how much apart are they? And so we've also just started to look at this, and also this seems to be quite interesting. Okay, yeah. So then I think I will end here and leave you with the movie again, so you can look at this these nice movies. And if you see, I think if you look at this at the very beginning, you see like where it like might go back. No, it's already started, right? So like, but it like really starts to form these like two on spiral just about that time, because there was like something passing by like here or so. Okay, thank you.
Yeah, okay, Robert.
Yeah, so this one is usually the beginning that when you say about the non-convergence, where this is identified as
Yes.
and
Should we do this first?
yeah,
Okay. Yeah, so I'm not claiming we have exactly figured this out, but so like there's several indirect arguments so first that you can look at. So first, there are like three obvious candidates you should consider immediately when you see something like this. The first one is whether something in your ISM model is not converged. Right? So we have this pressurized ISM model where we don't go into the details of any multi-phase structure. So we just say this is like pressurizing itself somehow magically with the supernova explosions and so on. And so we have an equation of state that above the star formation threshold of like 0.1 per cc, it just relates the pressure to the density. And maybe there are some systematic effects there that if you resolve the potential better, you go to higher densities, blah, blah. Right? We have tested this is not the case. The model actually works super well in that regard. So if you change the resolution just in the star forming gas, which you can also in a repo do very easily, you just say, okay, once you're then above a certain density, you change the target mass. It doesn't care. It really doesn't change in any systematic way. So it's not the ISM. Then the second thing you might think about is that if you go to higher resolution, you actually resolve the CGM better. And so that you might get like more cold clouds or so, and Fricke has shown that the higher resolution, you actually change the structure of the CGM, the circumgalactic medium, in some systematic ways. However, she has also shown that the galaxy really doesn't care at any of the resolutions we can go to. Even at the highest resolution that we have here, there's like level 2, 800 solar mass resolution baryons is like in the CGM comparable to like her 500 parsec run, so also, right? And at this resolution, the galaxy really doesn't care. So it's also not the CGM. Then you can worry about the AGN. So there's an AGN in the center, so the AGM is always fickle because it's a huge lever arm. Like you respond to you measure some kind of very local quantity, like the pressure and the density close to the black hole, which is completely independent of most of the disk and so on. And then you like put in energy by like just really directly calculated from this. And so if the density is like higher, you just put in more energy. And also you might imagine, so we already try to do this as well as possible by like to keep the to adapt with resolution there. By when we go to higher resolution, we actually measure all these properties in a sphere of the same mass. So then for the really high resolution simulations, we really take many cells into account to measure like the density and the pressure around the black hole. So to have a chance for convergence, right? Because if we just do like would fix and neighbors or so, we would just measure like at smaller and smaller radii, and you would expect some kind of trend. But essentially, we can show that this effect is completely there if you just run without AGMs. So if you just switch off the black hole, so it's also not the black hole. So what's really left then, and then you can think of why this is the main issue, is the disk-halo interface. It's really the transition region between the star-forming gas and the CGM. And I think my current understanding is the main issue is essentially that we never properly resolve the vertical pressure scale, right? And you can do a reasonable, like a rough estimate of like what resolution you would need for this and what mass resolution this translates to. And so even if you do like very optimistic estimates of like, I want to resolve the pressure, like one pressure scale height with like 3 cells or so, which like the mathematicians or so would tell you you're already in bullshit territory. But even if you want to do this, right, you need a mass resolution of 10 solar masses away. because it's low density material, 10⁻², and like the pressure scale height is maybe optimistically 150 parsecs. And it's just not resolved. So why is this a problem? It's a problem for the gas that falls on the disk. Because in a cosmological simulation, you don't not only have outflows, but you always have inflows as well. And the inflows come with quite some velocity because they're kind of falling down the potential. And what should happen then is they actually slow down when they're like running up the pressure gradient towards the disk. But if you completely don't resolve the pressure gradient, this happens like much less than it should, and the gas just falls through the disk and comes out again on the other side. And I think what happens here is that when we go to higher resolution, we still don't resolve the pressure gradient, but we do less poorly and less fully, and so we keep more of the gas that actually falls on the disk. And if this explanation is correct, I think this is a very general problem for all kinds of cosmological galaxy simulations, right? Because no one has the mass resolution to achieve this thing. Yeah, it's possible that it's also completely overshadowed by other things, right? It's
but that's great. The next question was, so you show all these galaxies kind of face on increase the resolution
yeah, the thickness is is quite well converged. So this is the vertical velocity dispersion at the solar position for those different variations, and this is like quite zoomed in on the x-axis. And so essentially also there, all of the things we do that's not changing the gas resolution give completely consistent results. It's also I think there was good arguments that there's a very also that if you change if the ratio between dark matter and stellar mass resolution, right, by too much, that you might like if the dark matter particles are too massive, they might numerically heat the stellar particles because they just interact with each other. This has been shown, this effect is clearly there. However, the amplitude of this effect scales not only with the ratio of these two masses, also just with the number of dark matter particles. Dark matter particles you have, the smaller number of things here. And already at the typical Auriga like standard resolution, or like TNG50 or like Firebox, if you plug just in the number of the dark matter particles you have at a typical halo, you're essentially on a time scale where this effect like takes a Hubble time to be relevant, right? So like you're essentially already says this. So in my understanding, this is really mostly an issue for the classical cosmological box simulations, right? For TNG100, I would worry about this. And because there you like the number of dark matter particles, even a Milky Way halo, is like so low. And then for TNG300, you really shouldn't look at these properties at all. And
okay, so let's give like some less senior person. Sorry. Okay. Yeah, let's Yindo. Thank you.
I was actually wondering about the philosophy, and you mentioned you basically haven't changed it at all, which, given that you're trying to the dynamics, seems very little, and I really expected you to find a lot of today, but if it doesn't matter about everything else, it's still like a revolution, so then could be this gravity is something really up with the other part of this.
So I think the question is, what do you exactly want to achieve, right? And so in the end, what the size of the structures you want to. So the critical part for us is typically we really want the softening to be large enough that we are sure that it's collisions for the whole time of the simulation, right? So we are relatively conservative in the softening choice to really make sure that two-body interactions are not happening in any meaningful way. Also because we just don't want to, like, we don't want to include this in any way, right? And so the question is then, yes, for what structures we would resolve with this better, right? And so like in the disk, so the ISM resolution for sure is not better, right? So we will not get smaller structures that because they formed and because they are there because the stuff on this, right? Like we don't have anything resembling molecular clouds whatsoever, right? So like any of those types of structures we just smooth over and don't have and will not go and ever claim to have, right? So we just don't model that. And then there might be an argument for if when satellites fall in the streams and so on, but even there I'm not entirely sure, because in the end, if you argue you would need a smaller softening there, then yeah, the question is with how many particles then would you trust this on the scale still, right? So you again, because these systems then have like of course for the disk itself, right? You might argue that you get away with a smaller softening and still be conditionless. But then if you have structures falling in that only have like 1 million particles, or 10 to the 5 or so, then you have to be much more careful again there, I think. So in the end, I think we tested this in many years ago quite a bit, like varying the softening, and never made too much of a difference. But I think in the end, we just went down the safe route here, where we know what's working, and that it works well, and just in doubt sacrifice like a slight little bit of resolution in certain structures. Might be worthwhile though, like, so these simulations are expensive, but not super expensive. So one of these Halos 2 redshift 0 is about 2 million core hours. So for instance, it's on a level where you can experiment with some of these things.
So it's presented and machine wants to ask a question. Okay. So Eugene.
All right. Maybe a good question about, do you have any satellites of Sagittarius mass there? And do they prefer these at the level that could be allowed to trace to this number of particles with previous like space spirals and stuff like that?
I don't know exactly. So there's like, we have 8 different Halos, right? And so we have like quite a variety in like satellite mass and so on. And I think there's 1 or 2 that also have like satellites that are more compared. Like one I think also has like a thing that's like similar to the sausage merger, but we have not specifically selected for satellite structures. We know already, and that's actually the single paper that's out already, that like we have like the phase space spiral. So like Rob Grant had a paper already where he used the very first test run that we did for this, that I showed before, also in part of the tests. That really shows very nicely this phase space spiral. And also there you see very nicely that at the normal resolution ones, that might even be there already, but you really don't see it. Like you cannot convince yourself it's there if you don't know it's there already, right? While then in the higher mass resolutions, it's just like a very clean signal. I think he has started looking into this, how general this is, like if this all of them have this, or like on some, but I don't know the exact.
So presenting and then Iran.
So where like the edge of the high-res region is in this So this is so there's no conceptual reason why it can't go there. Essentially what the way like this works in practice, right? So like the high-res region is large enough that anything that touches the main halo until redshift 0 is high resolution and always was high. So the background really doesn't, kind of like the halo is like sufficiently separates from the rest. So like it's like the background does not hurt you. The main limitation is just computational expense. And if you really want to go and like start like do like have like a reasonable estimate of like how star clusters form. So you not only need like much higher mass resolution, but then you also need the additional physics that's relevant on this scale. So in these simulations we just did. Okay? So then you really need to go into the details of the ISM structures and resolve them at enough resolution that you have a faithful representation of this. And so I think people have started to do this actually from the like a very high mass resolution. So they have solar mass resolution zooms, like cosmological zoom simulations, from different groups. And the main limitation there is they can only afford this for the tiniest ones. Right? They go there and pick a halo that is only 5 times 10⁹ solar mass at batch of 0. So, because then you can code a very high mass resolution or include all those things because the halo is so much smaller. But there's like a huge gap between doing this for like a small halo, and it's already super interesting, for example, for the plastic, exactly global plastic mission, so and doing this for because the maker is just so old.
Yeah.
We have not looked in detail into this yet, like this formation times, because the star formation histories are so similar. I wouldn't expect a big difference, but I haven't looked at it, so I'm willing to completely retract the statement if the situation is different.
I think we're out of time. Right, yeah. So thanks, really, again.